everyone. Now, I want to present our work on class-incremental learning with CLIP, adaptive representation adjustment and parameter fusion. What is class-incremental learning? Learning new classes. Class-incremental learning enables a model to learn and incorporate new classes incrementally as they appear, maintaining performance on old classes. Class-incremental learning aims to retain the model's performance on previously learned classes, even when access to old class data is limited. Our goal is to mitigate the forgetting of old classes while minimizing the computational cost of training the model. Our motivation has two parts. First, the CLIP model uses fixed text embeddings for classification. Besides serving as classifiers, these embeddings can provide additional information during training to mitigate forgetting. Second, parameters trained for each task can be finely fused to avoid an increase in parameter count and to retain both old and new knowledge. Overall, we add a trainable linear layer as an adapter after the CLIP image encoder, while freezing other modules. This strategy is divided into two parts: similarity screening and feature sampling. Before training, we use the text embeddings from CLIP to assess the similarity between current and past categories. This helps us filter and identify old categories that are similar to the new ones. We then sample simulated old categories using the mean and covariance of the features output by the pre-trained models corresponding to these categories. The sampled features are fed into the adapter, and we optimize using hinge loss to make them close to the text embeddings of the old categories and distant from those of the new categories. Layer fusion post-training. After completing the current task, we fuse the linear layer trained on the previous task with the one trained on the current task. First, we decompose the two parameter matrices into a linear space formed by a standard orthogonal basis. We then calculate the differences in the decomposed parameters to obtain fine-grained parameter weights and merge the decomposed parts. Finally, we restore them back to the original space. Since this is a post-training process, it consumes minimal time compared to training but effectively retains both new and old knowledge. The chart illustrates the relationship between the number of trainable parameters and the final accuracy on ImageNet 100. Our method requires only a single trainable linear layer while achieving state-of-the-art performance. As shown in the table, our method achieves the best results compared to both general pre-trained model-based methods and the proof method specifically designed for the CLIP model. This is the confusion matrices of the first 5 tasks in the ImageNet 110 tasks experiment and their differences. From Figure C, we can observe that our method effectively reclassifies the old class samples, which were misclassified as new classes in the baseline, back to their correct old classes. Thank you for your attention.